Okay, so here's where we were. We were taking our newfound theorem and appending it to our diagram of R3 calculus. And here it is. We found that the curl operator is our new piece of our onto our diagram, and the resulting curl theorem, Stokes' curl theorem, is that if you take a boundary of a surface and the curl of a vector field, then the resulting circulation and the resulting flux are equal. Okay. All right. So a couple of quick applications. So first, let's suppose we want to compute a line integral. All righty. We want to compute a line integral. Here's a vector field given, and here is a curve parametrized given. All right. So let's entertain our options. Right? So one thing we could do, now this is in fact a line integral. It's been parametrized. One thing I could do is plug and chug. Right? Chapter 5. Kind of always on the table in some sense. And you could do that. It would work, sort of. But I think it's going to be hard because keep in mind this parameterization is telling you x, y, and z. So you're going to have, as part of your integral, e to the power of sine t. And you're going to be dotting all of that business with x prime, which is going to have more trig in it. It's not that it's going to be that bad, but it doesn't look super convenient to do it that way. How about we use the fundamental theorem of line integrals? Right? Fundamental theorem of line integrals would be nice. All I'd have to do is take this vector field and find its antigradient. Fingers crossed. Optimistically, we hope. Keep in mind, we have to always worry about the possibility that the antigradient might not exist. Right? So you could play the antigradient game, and sadly, you will lose that game. There is no antigradient. Right? So now it's a reasonable thing to want to try in this case. I mean, so thinking in terms of you encounter this question on an exam. Thinking about the possibility that maybe you could find an antigradient and use the fundamental theorem of line integrals, that's a good instinct. It just wouldn't work in this case. Okay, so what is going to work is Stokes' curl theorem. Now, Stokes' curl theorem also has an asterisk. All of these boundary theorems have little asterisks to them. And this one here, the asterisk, if you're computing a line integral, if you're hoping to rewrite the line integral as a flux, the asterisk is that this does not apply to just any line integral. Notice it says right here, it's got to be a boundary line integral. It's got the same asterisk as Green's theorem. And again, this is not just a minor formality. It's very important that this be a boundary line integral because our accumulation argument was based on it being boundary line integrals, right? Boundary circulations. Furthermore, it really better be a boundary of something specific because we need to know that specific, what you might call anti-boundary, because that specific anti-boundary is the surface through which you need to compute a flux. Right, so this is no, issue of formality. This is not just, mathematicians getting upset about, microscopic details. If your curve is not a boundary of some surface, an actual surface, and it is the boundary of it, then this doesn't make any sense at all. It's just garbage. Okay, so we have to ask the very important question then, is this curve a boundary? Here's our curve, parameterized like that. It's that. And is it a boundary? Well, yes, it is. It's the boundary of this unit disk. Unit disk in the XY plane. Actually, maybe I better draw that a little bit more carefully, huh? So this is three-dimensional. Okay, so here's our axis system. Our curve here is like that. right? And yes, that is a boundary. It's the boundary of, I'm going to say, this disk here. But I will point out that that disk is not the only disk. Excuse me, that disk is not the only surface whose boundary is that curve. So now this is going to seem silly, but I just point out for your consideration, if I wanted to, I could use this half sphere. I could use the northern hemisphere, the northern unit hemisphere, right? The boundary of the northern unit hemisphere, same circle. So which should you use? I think a good rule of thumb is use whichever one's going to make your life most convenient, right? I mean, think selfishly. And in this case, I mean, come on. I mean, the flat disk has got to be easier, right? It's flat for one thing. It's easy to see what the unit normal vector is. It's really nice. Generally speaking, go with something flat if you have the option. But I will point out there are plenty of other options. So another thing you could do is you could imagine, like a glove. Right? Imagine a glove. Gloves have a hole down in sort of the wrist section where you put your hand through. That hole where you put your hand through could be that unit circle. You could have some glove-shaped surface. I can't imagine a scenario where that'd be a good choice. Nevertheless, something you can do. Okay. All right. So, so let's make this choice. We're going to choose this disk here. That's our new surface. You see here Gauss's divergence, Stokes's curl theorem. We're going to rewrite the circulation as a flux. Flux of what? Well, flux of the curl. Of course, that's what the theorem says. Got to take the curl of the vector field. This is just a calculation now, but the curl of this vector field, I'll do it like this. That vector field, compute the curl, and you get some nice convenient partial derivatives, some of which are 0, and you get 0, 0, 2. Okay, so you end up with a really nice integral, keeping in mind that the normal vector is easy to write down. This normal vector is 0, 0, 1. Right, keeping in mind that that normal vector sits inside of the ds. Right, like this. And notice the calculation falls together very nicely. Okay, questions? Everybody happy? Okay. Alrighty, let's try another one. So here we have a line integral. We want to compute. And we've got a vector field given. Vector field's not that bad, by the way. Pretty reasonable vector field. And let's see here, our curve. Now, our curve is not given parameterized. The curve is an intersection of that plane and that cylinder. Okay, so we need to draw a picture. Here's a reasonably representative picture. Our curve is the intersection of a plane with a cylinder. So something kind of like that. Now, if we're going to use Stokes's curl theorem, we are going to need to pick a surface. Can we think of, what's the easiest surface that we can think of who's got that as its boundary? Well, again, the obvious choice is to pick this solid ellipse. And let's think now, where does this solid ellipse come from? I appeal to your geometric intuition from the picture. That solid ellipse is part of this plane. Right? Just think about how the plane intersects that cylinder. The surface in the middle there is on the plane, not the cylinder. Everybody on board? You got to have the picture to be able to make that realization. That plane was given with this equation, therefore it has this as its normal vector. Oh, wait a minute, we need a unit normal vector. Apologies, this is a typo in the diagram here. That should be over the square root of 2 to make that a, let me make it better, 2. There we go. Make that a unit vector. Oh, hey, wait a second. We better think about orientations. Careful now, right? So let's see, what were we given about the orientations? It was given as that the curve is counterclockwise as seen from above. If the curve is counterclockwise as seen from above, then it goes around like this. And now you've got to ask yourself, there's two possible orientations on this surface. One possible orientation on this surface would be that it's oriented down. If it were oriented down, then think about your swirls with your right hand, and well, that induces the wrong orientation on the boundary. But the other possibility is that the surface is oriented up. Right hand swirls, that gives the correct orientation on that boundary. So you've got to play that game, right? You've got to consider the two different possibilities, two possible orientations on the surface. One induces the wrong orientation. One induces the right orientation. You have to pick the one that induces the right orientation. Everybody on board? Okay. So upward. Now, how do I tell that this is an up-ish orientation? Right? Maybe it's, how do I know it's not 1, 0, negative 1? Well, look at the third quarter. Right? You can see from the picture our options are one that's, this one here that's generally up-ish, and up-ish means the third coordinate's got to be positive. Okay. Alrighty. So, all that said, we're ready to apply Stokes' curl theorem right there. And the curl, not that bad to calculate. There's the curl, that vector field F. Right? Let's see, our normal vector, did I write down the algebra? Yeah, here it is. The normal vector, we agreed, was this right here, was negative 1, 0, 1 over the square root of 2. I just factored out the square root of 2. And so here's what Stokes' curl theorem gives us, right? Just, plugging and chugging straight with Stokes' curl theorem, we get this integral, and we get super lucky. Look how nice this is. You won't always get this lucky, but, I've arranged this example to work out nicely. Right? And dot product's clearly 0, and so the flux is 0, and we get 0. Everybody happy? Let me remind you, all of these theorems, Stokes' theorem, Gauss' theorem, Green's theorem, etc., these are not magic wands. These do not take questions and give answers. These take questions and give you instead different questions. Right? So what Stokes' curl theorem really did here is it turned one question into a different question. Now, in this case, it happened to be that this different question happened to be easier. Right? And that's nice when that happens, right? There's no promise that it will be. It's kind of like, I think of it as being kind of like the substitution rule. It's a good tool to have in your toolbox, and used appropriately, you do a substitution, make a clever choice, right? And you can hopefully turn a bad integral into a better integral. But you can use the substitution rule poorly. Right? And take a reasonably tractable integral and make a bad substitution and make a big mess out of it. Right? So that's also possible. So anyway, keep in mind, this is not always going to work out this well, but sometimes it will. Okay. All right, I'm going to let y'all read that example up there on your own. I want to go to densities again. Remember we interpreted divergence as flux density. I think it's pretty natural. Along those same lines, I appealed to your open-mindedness to reinterpret the derivative as change density. It's a weird way to think about the derivative, but pretty natural if you think about the analogy. Think about what we're actually doing with the fundamental theorem of calculus here, how we're generalizing it. And then likewise, with Green's theorem, Green's operator was circulation density. Okay. All right. So, is there a density point of view on Stokes' theorem? And the answer is kind of. So here's that point of view. Now remember, there's Stokes' curl theorem. right? This thing over here that we're computing, we've already discussed in the context of Green's theorem, we've discussed that this is circulation, that the vector field is representing a fluid flowing, and this going as it does around a boundary, this is what we might call boundary circulation. I'm just going to say circulation. So circulation is accumulating over the surface. And if it's accumulating over the surface, then this is what each little piece of accumulated circulation looks like. And here's a if we were going to make a density argument here about circulation, that is what you would have to call circulation density. So that's what gives circulation per unit area. Okay, and I want to zoom on this for focus. So this, what I have highlighted in green, is circulation density. This is the thing that you multiply by area to give circulation around that area. That's your density. And notice it's not curl. Awkwardly, right? So it's not. It's curl dot in. That orientation vector matters. Okay. So I want to make sense instead now out of, but what is curl by itself? Right? What is that thing specifically? And can I interpret that as a density? As of the moment, the answer is, well, nope, not yet, because right now our density is curl dot in. Okay. So before we go on with this question, I want to jump ahead to a hopefully familiar, different matter, and that is the fundamental theorem of line integrals. I don't know if y'all noticed this, but this was conspicuously absent in our previous discussion of densities. Right? When we were talking about Gauss's divergence theorem, I called back to several previous boundary theorems, and I talked about Green's theorem. I talked about, of course, we were talking about Gauss's divergence theorem, and then we talked about the fundamental theorem of calculus, and all of those we talked about the associated notion of density. Why didn't I talk about the fundamental theorem of line integrals? And the answer is because it's different. It's actually different in a way that's highly analogous to Stokes' theorem, so it's better to wait for this later discussion to bring this up. So let's talk about what that difference is. Here's fundamental theorem of line integrals. Let me rewrite the integral on the right-hand side there using this TDS notation that I hope you all remember. And so let's look at change being that integral. D-change is then that, which gives me that. So here's my notion of density in this context. That thing right there is what you multiply by size to get change. Right? Our change density, when you're looking at the fundamental theorem of line integrals, again, it's not gradient. It's gradient dot orientation vector. Right? Just like highly analogous to what we saw with Stokes' theorem. So what I'd like to do is, since gradient is something that we have more familiarity with, right? Change, it's a real simple formula, right? Something we can more easily see pictures of, right? I'd like to explore, but what is the gradient? In this context where we can see pictures, and then it's going to end up being highly analogous to that. Once we learn how to think about this, we'll be able to make more sense out of how to think about curl. Okay, so here's the idea. Suppose you have some function, and I'm going to draw some level curves of a function here. So these are those level curves. Here's f equals c1, and f equals c2, etc. Whoops. Etc. And let's consider a point there. And let's draw the gradient vector on this picture. What's the relationship between gradient and level sets? Well, they're perpendicular. So the gradient is let's see here. I guess I'll use red, I suppose. Here's the gradient. Key point is that is perpendicular. Okay. All right. So what's the gradient telling me in terms of density, in terms of change per unit distance? What does gradient tell us? Well, we know a couple of things about the gradient. We know that, not directly to the question, we know that the gradient points in the direction the function's increasing the fastest. Okay. But here's the more important point. By virtue of its magnitude, the gradient, by this magnitude, is telling us in that optimal direction, right? There's lots of different directions that you could move. You could be moving that way, you could be moving this way, you could be moving that way. Change per unit distance depends heavily on what direction you're moving. Oh, of course it does. But in that optimal direction, the magnitude of the gradient is telling you the change density. It's telling you change per unit distance in that optimal direction. In the optimal direction, the gradient's magnitude is the change density. So let me write that down a little bit differently. Gradient, the direction equals the direction of what I'm going to call most change. And it's telling you what direction change is really happening, right? When we say that the function is changing, the function's changing really that way. And then its magnitude is change density in that direction. Okay, so this is what I'm going to call an oriented density. And the idea is that it's not exactly a density, right? Totally, I know, absolutely. It's a vector, for crying out loud. Densities are scalars. Vectors can't be scalars. It doesn't make any sense. Right? But I'm going to call it an oriented density because it is telling you, look, you get right down to it, that change per unit distance is a complicated question when you have a function of multiple variables. Change per unit distance depends which way you're going. And until you tell me which way you're going, I can't tell you what your personal experience with change is going to be. If you don't tell me which way you're going and you just want to know how's the function changing, oh, well, okay. Look, that's the direction the function's really changing. The gradient tells you that. And how much is it changing as you go in that? What is the change density in that direction? Well, by the magnitude, the gradient tells you that. So the gradient is telling you, not knowing which way you're going, it's telling you everything you could possibly want to know about change density, including how much and what direction. Everybody see what I'm talking about? So I think this term oriented density is nice because it's giving you an orientation, namely the direction. It's indicating what's really happening. And it is furthermore, by its magnitude, telling you about the actual density in that direction. Okay. All right. So then you see that, how you recover what's actually happening in your personal experience. I mean, here we are moving along this actual curve. I'm moving in the direction of this actual tangent vector. Oh, okay. Well, now that we know what direction we're actually going, the oriented density, you dot with your actual tangent vector, that gives you your personal change density. So, curl behaves just like this. Curl is an oriented density. Curl is telling you, let's imagine a vector field representing again we have a fluid, and I appeal to your your sense of the physical. I'm going to make the fluid going around like this time, just to be consistent with the picture here. So the fluid is, there's a kind of there's a twisting, there's a swirling, circulating of the fluid like this. And okay, well, as I have it here, if I were to ask, in this scenario of the fluid flowing around like that, if I were to ask, hey, what's the circulation density? A pretty reasonable way to respond would be, oh, I don't know about your personal surfaces. I don't know what surface you're dealing with. Circulation around what boundary curves? You haven't told me what boundary curve you're going around. So you're just asking me about the circulation of this fluid by itself? Okay, well, here's the thing. This fluid is not just circulating randomly. It's circulating in a particular direction. It's circulating around this axis. It's not circulating that way. It's not circulating that way. It's circulating around this axis here like this. So the curl, by its direction, tells you around what axis the circulation is happening, and by its magnitude, the curl is telling you how much in some, in that, around, assuming that you're looking at circulation the right way, assuming that you're looking at circulation the way the fluid actually is circulating, the magnitude of the curl tells you how much circulation is, per unit area is happening around that direction. Okay, so notice that this recovers this same connection down here. So the curl, in some sort of absolute terms, is describing the circulation density. Well, circulation density has a direction. It's circulating a certain way. And if you want to know about your own personal, what are you going to get if you're looking at your own little piece of surface? If your boundary curve goes around a different way, right, then dot product with that normal vector recovers, how this affects you personally. So here's a picture example of that in action. This is intended to be two pictures of the same thing, the same fluid, that is. So we've got a fluid circulating around like this. Same thing, fluid circulating around like this. The curl is like that. Same fluid, same curl. Right now let's consider two separate boundary curves. Suppose you want to know, hey, how much is this fluid circulating around this boundary curve? Oh, hey, sweet. We're asking how much the fluid that's circulating like that, how much that fluid is circulating around this curve that's going around the same way. This is asking the question that this fluid wants to answer. I don't know if you see what I'm saying. We're asking how much the fluid is circulating around in a direction that the fluid is circulating. Right? So we're going to get a big answer here. There's a lot of circulation of this fluid around that boundary curve. And now, looking just at this picture here, again, you can see the fluid circulating around the same way the boundary is going. How do we actually get our hands on that? Well, the curl is describing the direction that the fluid is circulating. The normal vector is describing, in some sense, the direction that we're asking about. And notice that the coincidence, if you will, of the fluid circulating direction and the boundaries circulating direction is simultaneous with the coincidence of the curl's actual direction and the normal vector's direction. Whereas, by comparison, let's look at this picture. Suppose you're asking same vector field, same fluid, and you want to know to what extent, hey, is this fluid circulating around this way? The fluid is actually circulating around that way. So this fluid that's going around like that, to what extent is it going around like this? It's not really very much. right? It's not circulating around that way. It's circulating around this very different direction. So not much circulation is going to happen. Not much of a coincidence, not much of a pairing of the actual fluid circulation and the actual question that we're asking. And notice that that is likewise represented in how that curl vector and this normal vector are not pointing significantly in the same directions. So the dot product, curl dot in, is a way of getting our hands on to what extent is the circulation actually going around the way that we need it to be going around for the surface that we're interested in. In the same way that gradient dot t is a way of saying, and let me put a t vector on here just for comparison. The tangent vector t, if that's representing the direction we're actually going, right? Well, the function's changing a lot, but it's changing a lot in a direction that we're not actually going. We're going that way. The change is happening that way. This dot product is a way of us getting our hands on how much of the change represented by this gradient vector are we actually experiencing the way we're actually going. So again, with a dot product. So the geometry is very different between these two contexts, right? The geometry of the fundamental theorem of line integrals and how the gradient can be thought of as a oriented change density. Very different geometry than the geometry of how curl is thought of as an oriented circulation density. But the algebraic analogy is very strong there. So what I want you to do is try to use your intuition, try to use your, how much of a good intuitive sense you have for how gradient represents change, but how the dot product is required, right, to get the actual unit directional derivative in the direction you're actually going. Try to use your intuition and your sense of this to help you get a better idea of how curl acts likewise. Okay, it's a lot to say there. Okay, a couple of physics things I want to talk about. We're going to say less about this than we did in the Gauss context, but let's talk about magnetic fields. And let me draw a quick picture first. Magnetic fields. So again, you don't need to know much physics. But here is a fact. Here's a fact that y'all may have seen before. If you have a wire and if you have current flowing in the wire, then that creates a magnetic field flowing around the wire. I'm just curious if some of y'all have seen that in the past. Anybody taken Physics 151 before? So quick show of hands. Some of y'all probably, okay, half not. Okay, if you have not seen magnetic fields and currents before, no big deal. This is just a physics thing. Don't ask me why I didn't make the universe, right? But we have observed what happens if you have a wire and there's this thing called current, right? You can have charged particles flowing through a wire. The wire conducts electricity, you say. As the current flows through the wire, that way, the act of there being a current creates something called a magnetic field. And the magnetic field kind of goes around, it sort of wraps around the wire. And right hand rule, the thumb, the direction of the current, your fingers bending the way your fingers want to bend. Your fingers tell you the direction that the magnetic field wraps around the wire. Okay. That's just the world we live in. So, if you have a similar scenario, now instead of a straight wire, and the current is only flowing in the wire, and this is a safe little scenario that, we like to consider because that's, a lot of what we're going to see. A lot of how we deal with electricity is inside of wires, right? But if you had, hypothetically, a current of a flow of charged particles as a fluid And by the way, wires are not infinitely thin. If you have a microscope, if you look down at think about a wire as being like a great big tube that charged particles can flow through, you've got a current like that. Right? It's a flow of charged particles. So let's just entertain a flow of charged particles. Forget about the wire. Right? Well, this also creates a magnetic field. And the magnetic field, again, kind of wraps around in a way. And exactly how is something we're not going to worry about in this class. The details of, exactly what is that magnetic field. No comment exactly. But it sort of wraps around in this way. And you may notice that this picture kind of looks a lot like this picture, right, of curl. Curl, the vector field whose curl you're taking wraps around the curl vector. Right, so likewise, and again, this is just the world we live in. If this is your current field, if your current field, we use J very often to represent the current field. So remember, what we mean by a current field is a flow of charged particles. Charged particles are kind of a fluid. Water is a fluid, but let's not forget, it is in fact a bunch of little particles, right? So a flow of a bunch of particles can be thought of as a fluid. Fluids are represented with vector fields. Call this the current flow field. Then the magnetic field that is created flows around it like that, and notice that this, what we've drawn there, that the J field, right, is acting kind of like the curl of the B field. Okay, so again, this is just the world we live in. Again, don't ask me why I didn't make the universe, right? But this is what we observe. And there's a constant in there. Yeah, question.
Is this oriented in the correct direction?
Gosh, I hope so. We always have there's always that little Escher problem of which way did I mean here. So what I'm intending to suggest here is that the flow is going sort of up and to the right. That's pretty clear, right? And I'm intending to suggest that this magnetic field is, over here. This is kind of close on the bottom part of the B field over here. That this is close to us, and that this one here, this is sort of on the back side, if you will. So the B field is going around like that. Like the B field is going around like that, like my fingers. And notice my thumb going in the direction of the curl. That's what I was trying to draw, and it's easy to kind of see it backwards in the Escher kind of sense. One thing I'll point out about this, and I think this is weird, if you take a field, vector field, in this case B, right? You know B, you can compute its curl, and that gives you the curl field, which in this case is J. So we kind of tend to think about, when you're talking about curl, you tend to think of the B field coming first and the J field coming second. The thing you take the curl of, you have to know before you actually compute, is curl, you might say. Right? But we think of it kind of going the other way when you forget about curl, think about physics. The current creates the B field. The current creates the magnetic field. So what this is saying, if you take this sense of, look, current creates magnetism, and you come back down here to this curl equation, one way to think about this equation is that the current physically creates its own anti-curl, which is pretty wild if you think about it that way. And one of the reasons I think this is really interesting is you might have noticed that I didn't show you a formula for computing anti-curls. Right? We have a formula for computing, we have a process anyway, a game to play to find anti-gradients. Why not anti-curls? And the answer is that algebraically, it's really hard. It is beyond the scope of what we could reasonably do in Math 212 to algebraically find anticurls. But the physical universe does it automatically, and that's how the universe works. Flows of charged particles create the B field that is its anticurl. I think that's kind of a neat observation. Anyway, I like to point that out. Okay. So now we can do the usual, play the trick that we've played before, which is I'm going to take this equation and I'm going to, now instead of a triple integral, I'm going to take a flux of both sides here of this equation. Right, so the flux of the curl of the B field gives me that. And the flux of the constant times the J field gives me that. And let's think about what we have here. Stokes' curl theorem tells me that flux of curl is circulation. Right, so magnetic circulation. And now pulling this constant out, let's think about this right here. This is something that we can simplify in a straightforward manner. This J field, think about what that is. Remember, the J field just represents the flow of this. We've got this fluid of charged particles, and J is that the vector field representing that flow. So, rhetorical question: if I want to know a flux of a vector field that's representing a flow of a fluid, what is the flux of a vector field that represents the flow of a fluid? Well, this is where we motivated the idea of flux from. Flux is supposed to compute quantity of that fluid, amount of stuff per unit time. The stuff is charged particles. So this flux of a fluid flow is simply saying how much of the fluid, how much of the charged particles per unit time is passing through that surface. And charged particles per unit time is called current. If you've had a physics class and you know about current and related things, hopefully this will be familiar. If you do not know about current, if you haven't had a E&M class, no big deal. All this is quantity of charged particles per unit time. That's all it is. So again, we have these two different versions of this equation. Go back to this form. Yeah. So these are considered to be the same Maxwell's equation. These are very, very similar looking statements. This is about circulation, what you might call magnetic circulation. It's a circulation line integral at the magnetic field. So magnetic circulation. What is curl? It's circulation density. Well, oriented, but it's so in the oriented sense. This is the oriented density of that. So these equations really kind of just two different versions of the same equation. And again, the connection between them comes by way of knowing, in this case, Stokes' curl theorem instead of Gauss's divergence theorem. Okay. All right. There's a couple of quick things that you can say about the curl of the electric field. Don't worry about the physics here, but this is the curl of the electric field. And if you go through this same argument using Stokes' curl theorem, you can convert that into the integral version. So again, we have two equations that are really the same equation. So we have here the differential version and the integral version of the fourth of Maxwell's equations. Again, the specifics of the physics, don't worry about it. You're not responsible for that. Okay, so we are actually done with Stokes' curl theorem. So we're going to call it... we are done with page 438, thus putting us only 10 pages behind. But we do have, remember, we do have a sort of a buffer day in the schedule. Thursday is a little bit of a buffer, so we might have to cut into that buffer a little bit, it looks like, but we'll see. Okay, see y'all later.